Hello again. You might ask yourself or me what the point of having a data type of descriptions is. So let me show you one cool thing you can do with it if you have it, which is generic programming, because this is going to turn out to just be ordinary programming when you have a data type of descriptions. So here's a motivating example. In many of the courseworks, you've been asked to prove that certain things are propositions, right? Because this is sometimes useful to know. But it's tedious to do this over and over again. It would be nice if we could do it once and then be done with it, right? And that's exactly what you can do when you have a data type of descriptions. So let's see if we can do it. So remember that we had this data type of descriptions here, which describes our constructors. We have the args function, which turns a description into an actual thing. We have an argument, and we had the semantic bracket thing here, which actually gives you the data type that the description describes. So it has one constructor given by the arguments, and that's how you get the thing. Right. So now I would like to show that if I have a description, then the data type it described is always propositional. So of course this is not going to be true in general, because we saw that we could describe the natural numbers as a description. So we have to assume that all the types that we have in our sigma types, they were given by this universe U, themselves are propositional. So that wouldn't work for the natural numbers, because for the natural numbers we used the booleans, and the booleans are not propositional. It's not the case that every element of the booleans are equal. So we assume that we have this for the parameters of our thing, and then we can show that it holds for all our data types. And the way we typically do this is we prove the real thing on the arguments, and then here we can just instantiate it. So let's see that we can instantiate it first, perhaps. So what do we have? We have x and y that are in the described thing. So we can pattern match on x and y. We know that they are given by this sole constructor. Okay, so now x and y here, they come from the args, so we can use the real thing. Right, so first of all here you want con of something equals con of something, so let's use a con. And now here, if I do isprop args of d and x and y, I get exactly that x equals y. Right. So we see that the real work is going to be done by this function instead. And how do we do this? Well, we get an x and a y. We have to show that they are equal. And the way we do this is we pattern match on the code D. And then we see what we do for each case. Right. So it's going to clean this up a bit. Like that. Okay. So if the code is for the trivial thing, then we know that x and y must be TT in the unit type. So in this case, it's true. Okay, and let's do all the easy cases first. So here we know that x and y are from a product. So this is x comma y. This is x prime comma y prime. Okay, and now we want this pair to be equal to that pair. Well, if we do a con2, then we just need the components to be equal, and we can do that. Well, we might think that we can do that with a recursive call, right? But then we see that we have made a small mistake in our definition, because we only work with args where this d is the same as the d that you use here for the actual data type. But now when we move down, we see that this d stays the same, but this thing here has stayed fixed. So actually we have to generalize this. This is a common pattern where you might think that you want to do things with the same d, but you'll have more success if you generalize one of the D's to be something else. And this one is the one that's actually driving things, right? So that's the one I want to keep pattern matching on. This is just a parameter, so change that to a C. And then when I instantiate it down here, I'm going to choose C and D to be the same. But here when I go through it, I need to allow that one to vary. So now we see that this C stays the same, and we can apply X and X prime here. And it works. So that's a general pattern. Sometimes you have to generalize and make things more general. Things to go through. And then these recursive calls are fine. Right. Okay, and I think this one is also similar. So here we have two things from a sigma type. So let's call this one X comma Y. This one X1 comma Y prime. Okay. And now again, I want this pair to be equal to that pair, but now it's a dependent pair, so I can't just use a Kong2. It's the type of the second component depends on the first one. So first, I have to see that X equals X prime, but these are elements of A, and by assumption, all these ones are propositional, right? So if I use that fact, X and X prime, get something back. And now if I pattern match on this QQ, it has to be REFL. And then here I see that the first components are the same. So now I can do a Kong X comma. And now I need Y equals Y prime, and I can do this with a recursive call. What? Let's see. Yes. Okay, and finally here I have X and Y are from the interpretation of these things, so they must be con of X and con of Y for some X and Y. And I can peel off the con and do another recursive call here, I think. Yeah, where this underscore here really is the C, which we're not seeing, right? Okay, so by pattern matching on the code, we could prove this for all data types, right? Which is sometimes saving us a lot of time. And you can do the same thing with more complicated properties such as decidable equalities. You can show that natural numbers, lists of booleans, binary trees, etc. all have decidable equality in one fell swoop like this. It's a little bit more involved, but if you're interested, you can look at the code yourself, right? But it's the same pattern where you do the real work in a function for the args, and then you just instantiate it in a function for the actual data type. And again, you have to separate the C from the D that you actually pattern match on. So to summarize, you can do a lot of things by pattern matching on the codes. And this way you can write generic programs. Whereas in a language where you don't have dependent types in universes like this, then you can't do this. So in Haskell, you have the deriving mechanism, and it works fine for equality and show and OR, etc. But if you want to extend this to something else, then you're just out of luck because you have to go and extend the compiler. Whereas here, in a dependently typed language, we can just write this as ordinary programs, which is quite liberating.